My name is Ashton Whitfield, and this is my lab for Physics 2211, Lab Experiment 3, Black Hole. Introduction. Our layout and purpose of this lab. The purpose of Part 1 is to estimate the mass of a black hole by analyzing a star's motion, and the purpose of Part 2 is to use the calculated mass of the black hole to determine the necessary initial velocity for a spaceship to clear both the planet it is launching from and the black hole in order to exit the system. The overall purpose of our lab is to explore and understand the effects of Newton's second law and its interactions in relationship with momentum. Now for a preview of our results. For Part 1, we found the mass of our black hole to equal 1.86 times 10 to the 34 kilograms. And for Part 2, our initial speeds are seen here in the Glowscript code below. Models and principles. Our first important principle is Newton's second law as related to circular motion, which can be seen in this diagram here. To sum it up, the F-net is equal to the parallel and perpendicular components of the F-net. Now for our gravitational force. We can rearrange the equation for gravitational force to allow us to find the mass of our black hole. Other important equations are the velocity and position update formulas, which will be used to calculate the new position and velocity of our spaceship in our Glowscript code. Part 1 of our experiment, finding the mass of our black hole. Our Glowscript code model is as follows. The first bracket is initial conditions and constant values, and the second is our velocity calculation model, which was given to us. Now to the meat of our Glowscript code, finding the mass of our black hole. We have our final and initial velocities and momentums, the change in velocity and momentum, and the change in momentum over time. We established that our net force equals dp over dt, the rate of change of our momentum. Now we're calculating parallel net force. Now we calculate perpendicular force using our found parallel net force. Now we use our rearranged f of g equation to find the mass of our black hole. And now we update our star's velocity and position. Part 1 results. Our F-net is 1.00663 times 10 to the 29th Newton. Our parallel and perpendicular components are seen below, which add up to be our F-net, and the mass of our black hole is 1.85626 times 10 to the 34 kilograms, which is found using the average of all of our data points. Part 2. Here's our Glowscript code model for Part 2. This is our MBH, or the mass of our black hole from Part 1, our constants, and the max runtime. Here's our Glowscript code model Part 2. Rearranged f of g equation is seen here to find the planet's speed. Our initial conditions of our planet are seen here. To find our planet's orbital period, we use our circumference divided by our velocity times our time period. And our ship speed we found via trial and error. Glowscript code model. We're going to note the important equation for force of gravity. Finding the force of gravity from the black hole on the planet, we found the force of gravity from the ship on the planet, and then we found the net force of these two. We found the force of gravity from the black hole on the ship, finding the force of gravity from the planet on our ship, and then we did our position and velocity update for our planet and our ship respectively. Part 2 results can be seen in this video right here. I'm including only the last 10 seconds of this video, as the rest is kind of boring and it takes a while to run. But we can see that our ship exits our system. Possible sources of error for this lab are an imperfect model. We're using a model, and so we cannot account for outside forces, making this model imperfect and maybe not representative of real life. Trial and error. Our velocity for Part 2 was found via trial and error, and so there could be a more accurate initial velocity possible. Discussion. Our first part of our discussion is what does it mean? And the question for this part of our discussion is, in your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. The overview of our answer is they're the same. However, for our purposes, the rate of change of momentum is easier to calculate, as seen in this figure right here. The F-net is comprised of multiple unknown forces, where the parallel and perpendicular components of our dp/dt are easy to find. Now for the what-if portion of our discussion. The question for this portion of our discussion is, instead of wanting to take a quick look at the black hole and leave, you decide you want to enter into an orbit around the black hole. What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? Our velocity can be seen on the right and our orbit can be seen on the left. These velocities were found via trial and error, but they resulted in an orbit, so I called it a day. Thank you for watching!